When most people look at the Saturn V, they focus on its three enormous stages, its towering height, and the sheer scale of the hardware that lifted astronauts to the moon. But hidden between the towering rocket and the Apollo spacecraft sat a 1-meter-tall ring that actually flew the mission. This was the instrument unit. It formed the guidance brain and the nervous system of the entire launch vehicle, and without it, the Saturn V would have been nothing more than a stack of tanks and engines, with no ability to steer, regulate, or guide itself. The instrument unit was only 36 inches tall, yet it measured 6.6 meters in diameter. Its mass ranged between 2,000 and 2,100 kilograms, depending on configuration. But the true significance of the instrument unit was not its weight. It was the complexity packed inside this narrow aluminum honeycomb shell. Within that ring lived inertial sensors, a digital computing core, telemetry systems, environmental control hardware, precision cooling circuits, and electrical power. It was one of the most advanced pieces of avionics ever flown up to that time. The instrument unit was built around a cylindrical shell made from aluminum alloy panels. Each panel was nominally 0.95 inches thick. The ring was bolted to the forward skirt of the Saturn V third stage, the S4B stage, and to the adapter that held the Apollo command module and the lunar module. Because of this placement, the instrument unit carried all axial loads from the spacecraft into the third stage. It also carried bending forces caused by aerodynamic loads as the rocket passed through the dense lower atmosphere. Inside this ring, engineers arranged equipment around the inner circumference. Cold plates and equipment racks wrapped almost completely around the interior. Some racks were devoted entirely to measurement. 3 of these measuring racks sat at designated positions around the circumference, and each one held 20 plug-in signal conditioning modules. Across the full instrument unit, these modules supported hundreds of measurement channels. Every pressure, temperature, valve position, flow rate, acceleration, and electrical parameter needed for guidance and for post-flight evaluation passed through these racks. This entire structure had to endure extreme vibration, changing loads, and large changes in temperature, and it had to do so while carrying some of the most sensitive instruments ever developed for flight. Before the rocket left the pad, the electronics inside the instrument unit required strict thermal and environmental control. Pre-launch conditions could vary widely depending on weather, and condensation or contamination would have been catastrophic. So the instrument unit was connected to a purge system that delivered a stable mix of conditioned air and gaseous nitrogen. This regulated temperature and humidity and prevented the formation of corrosive films or frost. The instrument unit's environmental system was not simply a copy of the third stage system, but it was thermally coupled via ducting to the forward compartment of the S4B stage. Each section had its own defined purge loops and hardware, but the ducting and flow paths allowed the instrument unit and the forward S4B equipment volume to share a tightly controlled thermal environment. Hazardous gas sampling probes monitored the interstage area between the instrument unit and the third stage, looking for fuel vapors or other contaminants. This sampling system gave engineers a way to detect leaks or unexpected conditions even during the countdown and early ascent. To manage heat generated by the electronics, The instrument unit relied on a dedicated thermal conditioning system. This system circulated a coolant mixture of 60% methanol and 40% demineralized water. The coolant flowed through cold plates mounted beneath major instruments. These cold plates extracted waste heat from components like the digital computer, the inertial platform electronics, the telemetry racks, and the data handling equipment. The coolant temperature remained at about 59 degrees Fahrenheit, plus or minus 1 degree. In Celsius, that corresponds to 15 degrees plus or minus 0.6 degrees. Each cold plate could dissipate about 400 watts of heat under nominal conditions, and with up to 16 plates distributed across the instrument unit and its shared space with the S4B forward compartment, the system had considerable thermal margin. Some of these plates served equipment located in the S4B forward area, reinforcing the integrated nature of the design. On the ground, the coolant flowed through heat exchangers connected to external chillers, but in flight, the coolant released heat into space through a sublimation heat exchanger. This device exposed a thin layer of water to the vacuum of space. The water froze, then sublimated, and the vapor carried heat away. This method required no moving parts and worked reliably in the space environment. A dedicated branch of the environmental control system also supplied the extremely clean, stable gas-bearing flow required by the inertial platform. This integration of thermal management, inertial guidance, and environmental control was one of the signature engineering achievements of the instrument unit. At the core of the instrument unit's guidance capability lived the ST-124M3 inertial platform. This remarkable instrument was designed and built by the Bendix Corporation for NASA's Marshall Space Flight Center, and it was mounted on 3 gimbals and held fixed in inertial space. It measured the rocket's attitude and the forces acting upon it along 3 orthogonal axes. The gimbal design allowed essentially unlimited rotation about the X and Y axes and up to 45 degrees of travel about the outer gimbal, corresponding to motion about the Z axis. This prevented gimbal lock during the entire ascent. The platform carried 3 precision gyroscopes and 3 integrating accelerometers. The accelerometers measured the specific force along each axis of the vehicle and provided the raw data used to compute velocity and position. Before launch, the platform was aligned with remarkable precision. Engineers used matched pendulums riding on nitrogen gas bearings to set the platform's vertical orientation to within plus or minus 2.5 arcseconds of true vertical. To align azimuth, they used external optical prisms and a ground-based theodolite system that provided similar accuracy. All of this alignment work ensured that when the Saturn V left the pad, it began its flight with an inertial reference frame that was stable, accurate, and drift-free for the duration of the ascent. The inertial instruments depended on frictionless performance. For this, the instrument unit used precision gas bearings fed by ultra-clean gaseous nitrogen. These bearings allowed the gyroscopes, accelerometers, and alignment pendulums to float on thin films of gas. The bearing surfaces were machined to tolerances of around 20 microinches, or roughly 0.5 micrometers. The clearances between bearing surfaces were about 600 to 800 microinches, equivalent to 15 to 20 micrometers.
Gaseous nitrogen entered the bearing system at about 15 pounds per square inch and vented through a regulator that held the sealed internal environment at approximately 12 pounds per square inch absolute. The nitrogen supply came from a spherical pressure vessel with a volume of roughly 2 cubic feet, or about 56.6 liters, pressurized to 3,000 pounds per square inch. This tank provided stable flow throughout the ascent and was rugged enough to withstand the harsh vibration environment of the Saturn V. The gas bearing supply was fully integrated into the environmental control system, meaning temperature, flow stability, and purity were all controlled as part of one unified approach.
During pre-launch preparations, the inertial platform remained locked in place while the digital computer accepted mission-specific parameters. These included time markers for staging, engine cutoffs, and planned orbital targets. Immediately after liftoff, the Saturn V executed a pre-programmed tilt sequence. This initial tilt was necessary to begin the pitch-over maneuver that transitioned the rocket onto its eventual orbital trajectory. The tilt program was built into the guidance software and executed through engine gimbal commands. As the rocket ascended and aerodynamic forces decreased, the system transitioned into what engineers called iterative guidance. In this mode, the accelerometers aboard the inertial platform measured specific forces. The digital computer continuously integrated these forces to compute velocity and position. Every 2 seconds, the guidance algorithm updated the desired trajectory and generated new steering commands. In parallel, the attitude control chain received updates at a rate of 25 times per second. The launch vehicle digital computer produced guidance outputs that were passed through the launch vehicle data adapter, which then provided analog attitude correction signals at this 25 Hz rate. The computer core itself operated on its own instruction cycle, while the adapter and control interface delivered these higher rate corrections to the flight control electronics. This distinction between the internal computing cycle and the 25 Hz attitude update chain is an important nuance in how the system actually operated. During parking orbit and the subsequent restart of the S-4B stage for the translunar injection burn to place Apollo on its path to the Moon, the instrument unit continued to command engine gimbals and auxiliary thrusters to maintain attitude and execute the precisely timed burn required to place Apollo on its path to the Moon. The Launch Vehicle Digital Computer, developed by the International Business Machines Corporation, served as the computational heart of the instrument unit. It handled all autopilot functions, guidance updates, sequencing commands, telemetry formatting, and power routing from the moment of liftoff until the instrument unit was jettisoned. The computer operated on a master clock of 2.048 MHz and executed roughly 12,000 basic instructions per second. Simple arithmetic operations required around 82 microseconds. The memory consisted of ferrite cores arranged into 26-bit data words and 13-bit instruction segments. Although the system could support more than 32,000 words of storage, most missions used 16,384 words distributed across 4 memory modules. Most impressively, the computer's logic used triple modular redundancy. 3 identical logic paths ran in parallel, and hardware voters selected the majority result at each pipeline stage. This permitted a single failure without affecting the computation.
Over 250 hours of operation, the system achieved an estimated reliability near 99.6%. For a mission-critical guidance brain, nothing less would have been acceptable.
The launch vehicle digital computer produced digital commands that were converted into analog signals by the launch vehicle data adapter. These analog signals fed the flight control computer. The flight control computer was responsible for comparing the desired attitude with the measured attitude and generating the necessary control signals for engine gimbals and reaction control thrusters. Beyond steering, the instrument unit managed an intricate sequencing system that controlled valves, pyrotechnic devices, ullage operations, propellant dumps, and staging commands. These were executed through electronically addressed switch selectors. Inside the instrument unit, power distribution networks determined which equipment racks were energized during specific phases of the mission. This allowed mission planners to minimize power consumption while ensuring that critical hardware always remained powered.
The instrument unit monitored a vast array of parameters: accelerations, angular rates, pressures, temperatures, valve positions, electrical flows, and frequencies were all measured by transducers. These signals entered the measuring racks, where the conditioning modules standardized them, usually into a 0 to 5 volt range. Transmission used several techniques. For analog data, the system used pulse amplitude modulation. For high-accuracy digital data, it used pulse code modulation. Other techniques included pulse code modulation on frequency modulation on frequency modulation, and single sideband frequency modulation. These formats fed very high-frequency transmitters connected to omnidirectional antenna arrays. The arrays provided roughly 20 watts of effective radiated power and maintained communication through roll maneuvers and other attitude changes.
Before launch, the telemetry signals flowed into ground-based digital data acquisition equipment through coaxial cables. Engineers could remotely calibrate selected channels using the remote automatic calibration system. This system injected known reference voltages into modules to verify accuracy. During flight, the instrument unit used data storage equipment, a tape recorder using half-inch magnetic tape, to capture telemetry when radio communication could be interrupted. This recorder provided on the order of 30 minutes of continuous recording capacity and covered frequencies ranging from a few hundred hertz to tens of kilohertz. It ensured that no critical information was lost during staging, plume-induced signal blackout, or other short communication gaps. Telemetry packets were time-tagged so that ground analysts could reconstruct the vehicle's exact performance, reconstruct its state vector, and evaluate every subsystem after the mission. The electrical power system depended on 4 silver-zinc primary batteries. 3 were housed inside the instrument unit, and the 4th was mounted within the S4B stage. The system delivered a nominal 28 volts direct current, with each battery providing roughly 350 ampere-hours of capacity. Converter assemblies generated a 5-volt direct current reference used for transducers and telemetry calibration, and a 56-volt direct current supply that powered the inertial platform and associated excitation systems.
Power routing logic ensured that non-essential loads could be disconnected in emergencies, preserving guidance and control hardware. The entire power system was sized to support around 250 hours of operation, far longer than any mission required, but essential to provide redundancy and safety margin.
When engineers designed the instrument unit, they knew one thing for certain. If this ring failed, the mission was lost. The rocket could not steer itself without the inertial platform. It could not compute its trajectory without the digital computer. It could not sequence its stages, monitor its performance, maintain its thermal environment, or downlink data to Earth. This is why the instrument unit was engineered with such deep conservatism and such generous margins. Thousands of watts of cooling capacity, hundreds of ampere-hours of electrical reserve, multiple telemetry paths, triple redundant logic, precision inertial instruments floating on nitrogen gas bearings inside a carefully regulated 12 pounds per square inch environment, all locked together into one tightly integrated load-bearing ring. This was the true flying brain of the Saturn V. A 1-meter-tall band of aluminum honeycomb that held some of the most advanced avionics ever developed. Without this ring, the rocket would not have reached orbit. Without this ring, the translunar injection burn would not have been possible. And without this ring, Apollo would never have reached the moon. If you enjoyed this look inside the Saturn V's instrument unit and the engineering that made Apollo possible, consider giving the video a like and sharing it with someone who appreciates real spacecraft hardware. It truly helps the channel grow. And if you want to support more videos on the systems that flew astronauts to the moon, you can join the channel for early access, badges, and members-only content. Thanks for being part of this mission.